There is a place in the universe where time itself seems to hesitate, where the ordinary laws governing everything you have ever touched, everything you have ever seen, everything that has ever existed in the world you know, bend toward their breaking point and then break. It is not a black hole. It is not a void. It is something stranger in its own way, something that sits at the border between existence and annihilation, spinning in the dark at hundreds of revolutions per second, radiating energy across thousands of light years, carrying inside its impossibly small body a secret that physicists have spent decades trying to crack open. It is a neutron star, and the story of what lives inside one is among the most dramatic, most humbling, and most unsettling stories that the universe has ever told. If this kind of journey into the deep unknown moves you, it would mean the world to us if you liked this and subscribed. To begin to understand what a neutron star is, you have to first understand what everything else is. You have to start with the matter you are sitting inside right now. The matter that makes up your chair, your walls, the air you are breathing, your own body. Because the story of a neutron star is ultimately the story of what happens when that matter is taken to the absolute edge of what it can endure, when the universe decides to find out exactly how far it can push before everything comes apart. Matter, as you experience it, has a texture. It has weight and solidity and resistance. When you press your hand against a table, it pushes back. When you hold a stone, you feel its heft. When you breathe in, your lungs fill with something real, something physical, something that occupies space. All of that experience of solidity and substance rests on a structure so delicate and so improbable that it seems almost miraculous it holds together at all. Every solid thing in the observable universe is constructed from atoms. Each atom is a miniature architecture of almost unimaginable fragility. At its center sits a nucleus, an extraordinarily dense cluster of protons and neutrons held together by the most powerful short-range force in nature. Around that nucleus, at distances so vast relative to the nucleus itself that the comparison strains the imagination, electrons orbit in their quantum shells. If you were to scale a single hydrogen atom up until its nucleus was the size of a marble sitting in the middle of a football pitch, the electron associated with that atom would be somewhere in the distant parking lot outside the stadium. The entire interior of that stadium, every cubic inch of it, would be empty. Not mostly empty, not nearly empty, empty. This is the reality hiding underneath the illusion of solidity. The chair beneath you, the floor below that, the planet beneath the floor, all of it is almost entirely empty space. The sensation of solidity, the reason your hand does not pass through the table, is not because matter is packed tightly together. It is because the electron clouds of adjacent atoms generate electromagnetic repulsion. The electrons push back. The force between electron clouds is what creates the illusion of a solid world. Matter is, in a very real sense, held together by stubbornness, by the quantum mechanical insistence of electrons that no other electron shall occupy the same state. This is a crucial thing to understand before you descend into a neutron star, because a neutron star is what happens when that stubbornness fails. When gravity grows powerful enough to overcome the electromagnetic resistance of electron clouds, to drive electrons into places they were never designed to go, to strip away the architecture of atomic structure and replace it with something that has no counterpart anywhere in ordinary experience. The neutron star is what the universe looks like when it decides to compress matter not just past the point of comfort, but past the point of recognition. To understand how a neutron star comes to exist, you need to understand where stars come from and what they truly are beneath their light. A star is not simply a ball of fire. Fire is a chemical process, a rapid oxidation, a phenomenon that requires the presence of already complex molecules and atmospheric oxygen. Stars are something far older, far more primal. They are the universe's primary mechanism for converting gravitational energy into light and heat. They are, at the deepest level, a temporary truce between two forces that want opposite things. Gravity wants to pull everything inward. It has always wanted this. From the first moments after the universe began and hydrogen and helium began to pool together in vast clouds across the cosmos, gravity was already at work, drawing particle to particle, accumulating mass, building density. Given enough time and enough material, those clouds grew dense enough that the temperature and pressure at their centers climbed to extraordinary heights. At some threshold, the temperatures became hot enough that atomic nuclei could be forced close enough together that a different force, the strong nuclear force, could reach out and bind them. Hydrogen nuclei fusing into helium, releasing energy in the process. This is the moment a star is born, not when it first begins to glow, but when fusion ignites in its core and the energy released begins to push outward against the inward pull of gravity. For most of a star's life, this arrangement holds. Gravity squeezes inward, fusion energy pushes outward. The star achieves a kind of dynamic equilibrium. Not static, not frozen, but balanced. Our own sun has been living inside this balance for roughly 4.5 billion years. Deep in its core, where the temperature reaches around 15 million degrees Celsius, and the pressure is roughly 250 billion times what we feel at sea level on Earth, hydrogen is being transformed into helium at a rate that would seem catastrophic on a human scale. Every second, the sun fuses roughly 600 million tons of hydrogen. Every second, about 4 million tons of that mass is converted directly into energy according to the most famous equation in physics. That energy works its way outward through the sun's interior, radiating eventually into space, warming planets, making photosynthesis possible, sustaining life across 150 million kilometers of vacuum. But stars that are significantly more massive than the sun live a different life, and they die a different death. A star with 10 or 15 or 20 times the sun's mass is a different kind of engine. Its gravity is so much stronger that it squeezes its core to much higher temperatures and pressures. The fusion reactions proceed far faster. The fuel burns at a furious rate. Where the sun will burn steadily for 10 billion years, a star 20 times as massive might exhaust its hydrogen in only a few million. That's not 10 times shorter. That is thousands of times shorter. These massive stars are living fast and burning bright, spending their energy with a profligacy that makes the sun look miserly. And when the hydrogen runs out, the story doesn't end. For massive stars, the end of one fuel is simply the beginning of a new and more desperate phase. The core contracts under gravity, which heats it further, until the temperature rises high enough to fuse the next element in the chain. Helium fuses into carbon and oxygen. When helium is exhausted, carbon ignites, then neon, then oxygen, then silicon. Each successive fuel requires a higher ignition temperature than the last. Each successive phase burns faster. The hydrogen phase lasts millions of years, the helium phase hundreds of thousands. Carbon, a few centuries. Oxygen, perhaps a year. Silicon, a single day. Think about the compression of that timeline. Millions of years of stable burning, then hundreds of thousands, then centuries, then a year, then one day. The star is collapsing forward through time, racing toward an ending it cannot escape. And at the end of that single frantic day of silicon burning, the core fills with iron. And iron is where everything stops. Every element lighter than iron releases energy when fused into heavier elements. This is why fusion works as a power source for stars, why it has kept them burning for billions of years. But iron is the exception. Iron sits at the minimum of nuclear binding energy. Fusing iron does not release energy, it absorbs it. When the iron core reaches a critical mass, roughly 1.5 times the mass of the sun, packed into a sphere the size of Earth, the thing that has been holding the star up for millions of years simply disappears. The fusion energy source vanishes. And what gravity has been holding at bay for so long is suddenly unleashed. What follows happens in a fraction of a second. The iron core, no longer supported against gravity, collapses. It falls inward at 1/4 of the speed of light. In roughly 1/10 of a second, a sphere the size of our entire planet crumples down to an object perhaps 12 kilometers across. 12 kilometers. The distance you might drive to reach a neighboring town. And into that 12-kilometer sphere, all the mass of a stellar core, more mass than the entire sun, is being compressed. The violence of this event is beyond any human framework for comparison. No explosion, no earthquake, no volcanic eruption, no asteroid impact approaches anything close to the energy scales involved. The gravitational energy released during the collapse of a stellar core in those few seconds exceeds the total energy output of the sun over its entire 10 billion year lifetime. Not by a small margin, The core collapse outproduces the sun by many orders of magnitude in those few devastating moments. Most of that energy is carried away immediately by neutrinos, particles so ghostly and so reluctant to interact with matter that they can pass through a light year of lead as if it were air. The neutrino burst from a collapsing stellar core is one of the most extraordinary phenomena in the known universe. For a few brief seconds, a single dying star radiates more energy in neutrinos than all the hundreds of billions of stars in its galaxy are radiating in light, combined. Every star in the galaxy, the entire luminous output of 100 billion suns, is overwhelmed by the neutrino flash of a single death. We actually detected this once. In 1987, a massive star in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way about 168,000 light-years from Earth, underwent exactly this kind of collapse. Detectors in Japan and in the United States, buried underground to reduce interference from cosmic rays, registered a total of about 25 neutrinos, just 25 particles, out of the incomprehensible torrent that washed through the Earth. But that handful of detections confirmed decades of theoretical prediction. It was the moment we proved that we understood, at least in broad terms, how these extraordinary objects are born. The outer layers of the star, which had been falling inward, slam into the newly compressed core and bounce. The shock wave that results tears through the star's outer envelope and blows it apart in a supernova explosion. For weeks, that single stellar remnant can outshine every other star in its host galaxy. The light from a nearby supernova, if one happened close enough, would be visible in daylight. It would cast shadows at night. It would be one of the most dramatic events any human civilization had ever witnessed. But the explosion, spectacular as it is not the point. The explosion is the star's death rattle. The point is what it leaves behind. At the center of all that destruction, the collapsed core continues to compress, to solidify, to become something that the universe has only a handful of ways to create: a neutron star. The neutron star that emerges from this crucible is an object so strange that describing it in familiar terms requires a constant reaching for analogies that always fall slightly short. Its diameter is roughly 12 kilometers. Its mass is between 1.5 and 2 times the mass of our sun. This means that into a sphere you could walk across in a few hours, the universe has packed the equivalent of 500,000 Earths. The resulting density staggers description. A single teaspoon of neutron star material, a volume smaller than a die on a board game, would weigh somewhere in the vicinity of 400 million tons. Not 1,000 tons, not million tons, 400 million tons. The Great Pyramid of Giza, one of the most massive structures that human civilization has ever assembled, weighs roughly 6 million tons. A teaspoon of neutron star outweighs it by a factor of nearly 70. If you could somehow hold that teaspoon and then let go, it would not fall to the floor. It would fall through the floor, through the foundations of the building, through the bedrock beneath, through the crust of the planet, through the mantle, straight to the core. Nothing on Earth has the structural integrity to resist that density. The gravity at the surface of a neutron star runs to roughly 200 billion times the surface gravity of Earth. On Earth, gravity accelerates falling objects at about 10 meters per second squared. On a neutron star, the same object would accelerate at roughly 2 trillion meters per second squared. A person weighing 70 kilograms on Earth would weigh approximately 14 trillion kilograms on the surface of a neutron star. The body would not merely be crushed, it would be smeared into a film of atoms a fraction of a millisecond after arrival, flattened by forces that exceed any conceivable structural resistance. The magnetic fields of neutron stars are, if anything, even more extreme relative to human experience. A typical neutron star carries a magnetic field roughly 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, push this further still, to 1 quadrillion times Earth's field strength. At those intensities, the magnetic field becomes strong enough to alter the structure of individual atoms, distorting their electron clouds into elongated cylinders aligned with the field lines. At the surface of the most powerful magnetars, the field becomes strong enough to affect the vacuum of empty space itself, causing it to behave as a polarizing optical medium and bending the paths of photons passing through it. Neutron stars also spin. They spin because the stellar cores from which they collapse were already rotating, and when you compress a rotating object, angular momentum is conserved, the same principle that causes a figure skater to spin faster as they pull their arms inward, operates here, but at extraordinary scale. A stellar core that was rotating perhaps once every few hours or days becomes, upon collapsing to city size, a neutron star rotating many times per second. Some neutron stars, those that have been spun up by accreting material from a companion star over millions of years, rotate hundreds of times per second. The fastest known example spins at 716 revolutions per second. The surface at its equator is moving at a significant fraction of the speed of light. In the time it takes a human being to blink, this object has completed more than 200 full rotations. The combination of rapid spin and powerful magnetic field means that many neutron stars emit focused beams of electromagnetic radiation from their magnetic poles, sweeping those beams around the sky like cosmic lighthouses. When the geometry is right and one of those beams sweeps across Earth with each rotation, we detect it as a regular pulse of radio waves. These objects are called pulsars, and their timing is so precise that the first astronomers to detect them in 1967 were seriously uncertain whether they might be receiving signals from an artificial transmitter. The pulses were too regular, too consistent, too precise to seem natural. The initial designation for the first discovered pulsar was LGM1. LGM stood for Little Green Men. The precision was that unsettling. But the most extraordinary thing about a neutron star is not its surface properties, not its spin, not its magnetic field, not its gravity, dramatic as all of those are. The most extraordinary thing is what lives inside, what matter becomes when it is compressed to these densities. What happens to the familiar architecture of atoms when the universe squeezes them past every limit they were ever designed to withstand? To understand the interior of a neutron star, you need to make a journey inward, layer by layer, watching as the familiar dissolves and the strange takes over. You need to start at the surface and descend, witnessing at each stage a new transformation of matter into something that has no counterpart in any laboratory on Earth, no equivalent in any everyday experience, no name in ordinary language except the names that physicists have invented to describe things they have never directly seen. The outermost layer of a neutron star is its atmosphere. It is thin, perhaps a few centimeters to a meter, a gossamer film stretched over an object of almost incomprehensible density. The atmosphere is made of ordinary atoms, mostly hydrogen and helium, and it is extraordinarily hot by any everyday measure, perhaps 1,000,000 degrees. But compared to what lies beneath it, this outermost skin is almost quaint. It is the last place on the entire neutron star where anything resembling the matter you are made of can survive. Below it, the familiar begins its long, irreversible dissolution. Beneath the atmosphere lies the outer crust, a layer perhaps a few hundred meters deep. Here, the pressure has already grown sufficient to strip every atom of its electrons completely. The atoms are fully ionized, meaning the electrons have been separated from their nuclei by the crushing gravitational pressure and exist as a dense, free-floating sea rather than as clouds bound to individual nuclei. The bare nuclei, stripped of their electron shells, arrange themselves into a crystalline lattice, a regular, repeating geometric structure reminiscent in principle of the crystal lattice of ordinary metals, though the comparison is more poetic than literal. The spacing between nuclei is vastly smaller, the pressures incomparably greater, and the nuclei themselves bear no resemblance to anything found in any metal you have ever handled. These nuclei are neutron-rich to a degree that would render them wildly unstable under any ordinary conditions. In the crust of a neutron star, the crushing pressure forces protons to capture electrons in a process called inverse beta decay. An electron and a proton collide with sufficient energy that the weak nuclear force can convert them into a neutron and a neutrino. The neutrino escapes, the neutron stays. Over time, nucleus after nucleus in the crust is transformed, gaining neutrons and losing protons, becoming increasingly unbalanced by any earthly standard. On Earth, the periodic table contains a fixed set of stable isotopes: iron with 26 protons and 30 neutrons, carbon with 6 of each. nickel and selenium and krypton in their familiar forms. In the outer crust of a neutron star, the equivalent isotopes might have the same number of protons, but 2 or 3 times as many neutrons. They would exist nowhere in the natural world outside these extreme environments. Under any ordinary conditions, they would decay in fractions of a second, shedding neutrons through radioactive emission. Inside the crust, the pressure prevents their decay. There is nowhere for the extra neutrons to go. They are held in place by circumstance, exotic isotopes, stabilized by force rather than by nuclear harmony. As you descend deeper into the outer crust, the nuclei grow more and more neutron-rich with each additional 100 meters. The ratio of neutrons to protons climbs steadily, and then, at a depth of perhaps a few hundred meters and a density of roughly 400 trillion kilograms per cubic meter, you reach one of the most important boundaries in the entire structure, the neutron drip point. The neutron drip point is the depth at which nuclei have become so saturated with neutrons that they physically cannot hold anymore. The strong nuclear force, which binds nucleons inside a nucleus, has a limit to how many neutrons it can accommodate relative to the number of protons. When that limit is exceeded, neutrons begin to leak out of the nuclei like water overflowing a glass. They drip into the space between the nuclei, becoming free particles rather than bound ones. Below this boundary lies the inner crust, and the inner crust is a place unlike anything in the terrestrial world. In the inner crust, 3 populations of particles coexist simultaneously in the same volume of space. There are the nuclei, still present but growing ever larger and more bloated as you descend. There is the electron sea, still providing some pressure and some support. And now there is also a gas of free neutrons, wandering through the spaces between the nuclei, unattached and unconfined. This free neutron gas grows denser as you go deeper. At the neutron drip point, perhaps only a few % of the neutrons are free. Deeper down, the fraction climbs. 10%, 20, 50. The nuclei are being literally drained from outside, shedding neutrons into the surrounding gas, growing simultaneously more neutron-rich and more depleted as the environment pulls neutrons away faster than inverse beta decay can replace them. The nuclei themselves are growing enormous. On Earth, the largest stable nucleus is lead-208, containing 82 protons and 126 neutrons. In the deep inner crust of a neutron star, nuclei might contain hundreds of neutrons, bloated into structures that would be considered freakish by any nuclear physicist studying them in isolation. But they are not in isolation. They are held in place and held together by the overwhelming pressure of their environment, which prevents their decay and forces stability on configurations that have no right to be stable. And then something remarkable begins to happen. As you descend toward the boundary between the inner crust and the core, the geometry of the nuclear material begins to change. The shapes that nuclei form in this transition zone are so extraordinary that physicists have given them names drawn from an unexpected corner of culinary vocabulary. At moderate depths in the inner crust, the nuclei are roughly spherical, as you might expect. Surface tension from the strong nuclear force pulls nuclear matter into spheres, minimizing surface area and surface energy. These roughly spherical blobs of dense nuclear material sit embedded in the surrounding neutron fluid, and physicists call this the meatball phase, because the picture is essentially that of spherical lumps of nuclear matter floating in a less dense medium. As pressure increases and density rises, the spheres grow larger and crowd closer together. At some critical density, it becomes energetically favorable for the spheres to elongate and merge into long cylindrical tubes, rods of dense nuclear material running through the neutron fluid. This is the spaghetti phase. The geometry has shifted from zero-dimensional blobs to one-dimensional strands because the balance of forces has tipped. The competition between the strong force's tendency to draw nuclear matter together and the electromagnetic repulsion between the positively charged protons in the nuclear material has shifted the optimum shape. Go deeper still, and the cylinders begin to merge in a second direction, forming flat sheets of nuclear material separated by layers of less dense neutron fluid. This is the lasagna phase, a layered structure of alternating dense and diffuse material that, if you could somehow see it, would look nothing like the kind of matter you have ever encountered. At even higher densities, the geometry inverts. Instead of dense nuclear matter forming structures embedded in a neutron fluid, the neutron fluid begins to form structures embedded in the nuclear matter. Cylindrical tubes of neutron fluid running through a continuous nuclear medium, like hollow pasta. Then spherical bubbles of neutron fluid embedded in solid nuclear material, like holes in Swiss cheese. And then, at the highest densities of the transition zone, the bubbles shrink and vanish, and you are left with a continuous uniform nuclear fluid with no internal structure at all. The crust is over. The core has begun. Nuclear pasta sounds whimsical. The naming is, admittedly, delightful, but the physics behind it is entirely serious. These structures arise from a genuine and precise competition between fundamental forces operating at densities that no laboratory can replicate. They are not metaphorical shapes or approximate descriptions. Theoretical calculations predict them with mathematical rigor, and their properties have real consequences for neutron star behavior. Nuclear pasta is calculated to be among the strongest materials in the universe, perhaps 10 billion times stronger than steel. Not because of any exotic new physics, but because its structure is held together by the strong nuclear force itself, the most powerful short-range force known. Breaking a sheet of nuclear lasagna would require overcoming the strong force's grip on every nucleon in the structure. The energy required would be extraordinary. The pasta phases also affect how newly formed neutron stars cool in the hours and days after their birth, and how the crust of an older neutron star responds to mechanical stress, which in turn affects the observable behavior of the star. Understanding these exotic structures is not merely an academic exercise. It is directly relevant to interpreting the signals we receive from pulsars across the galaxy. But now the crust has ended. The last nuclei have dissolved into each other, their boundaries vanishing as the space between them shrinks to nothing. There are no more individual nuclei. There are no more atoms in any meaningful sense. The electron clouds are gone. The atomic architecture that underlies all chemistry, all molecular biology, all material science has been completely and irreversibly dismantled. What remains is something else entirely, a continuous ocean of nuclear fluid, stretching from just below the surface all the way to the center of the star. In the outer core, which begins at the base of the crust and extends inward for several kilometers, the composition of this fluid is relatively well constrained by our current understanding of nuclear physics. The matter is overwhelmingly neutrons, roughly 90 to 95%. The remaining 5 to 10% is split between protons and electrons in roughly equal numbers, with the electrons maintained to balance the electric charge of the protons and keep the whole system electrically neutral. This neutron dominance is the result of thermodynamic equilibrium. If there were too many protons relative to neutrons, the inverse beta decay process would convert protons and electrons into neutrons until the balance shifted. If there were too few protons, ordinary beta decay would convert neutrons back into protons and electrons. The system settles into a stable composition at which both processes are in balance, and at the pressures found in a neutron star's outer core, that balance point favors neutrons overwhelmingly. In an ordinary atomic nucleus, the ratio of neutrons to protons is roughly 1:1, or slightly more neutrons than protons. In the outer core of a neutron star, the ratio is closer to 19:1. The matter has been transformed almost completely. The vast majority of the protons that existed in the original star have been converted into neutrons by the relentless application of pressure. What holds this object up against its own gravity? In the outer core, the answer is primarily neutron degeneracy pressure, supplemented by the repulsive short-range component of the strong nuclear force. The first of these is conceptually analogous to what holds up a white dwarf, but operating at densities roughly 1,000,000 times higher. Neutrons, like electrons, are fermions, meaning they obey the Pauli exclusion principle, the quantum mechanical rule that no two identical fermions can occupy the same quantum state simultaneously. As you compress the neutron fluid, neutrons are forced into increasingly energetic quantum states because the lower states are already occupied. This forced occupation of high-energy states generates an outward pressure that resists further compression. It is a purely quantum mechanical effect, requiring no heat, no energy input, no ongoing process. It arises simply from the impossibility of stacking fermions on top of each other in quantum state space. But neutron degeneracy pressure alone is not sufficient to explain the stability of neutron stars. Unlike electrons in a white dwarf, which interact primarily through electromagnetism, neutrons interact through the strong nuclear force, and the strong nuclear force changes the picture significantly. At the densities found in the outer core of a neutron star, every neutron is within the range of the strong force of essentially every nearby neutron. The average separation between neutrons is comparable to the range of the strong force itself, roughly 1 femtometer, 1 quadrillionth of a meter. The neutrons are all simultaneously within reach of each other, interacting constantly through a force that is both attractive at moderate range and strongly repulsive at very short range. It is this short-range repulsion that prevents the star from collapsing further. As the neutrons are squeezed ever closer together, the repulsive component of the strong nuclear force grows stronger and stronger, pushing back harder and harder against the crush of gravity. The neutron star maintains its 12-kilometer size not because anything is preventing gravity from acting, but because at this density, the combined pressure of neutron degeneracy and strong force repulsion exactly balances the gravitational pull of two solar masses of material. The outer core is also, it appears, a superfluid. A superfluid is a state of matter in which viscosity, the internal friction that causes ordinary fluids to resist flow, drops to exactly zero. Superfluidity is not an approximation or a limit. It is a precise quantum mechanical state in which the fluid flows without any energy loss whatsoever. Set a superfluid in motion, and it will flow forever, without slowing, without losing energy to friction, without dissipating. It is one of the most remarkable and counterintuitive phenomena in all of physics. Superfluidity in neutron star cores arises through a mechanism called Cooper pairing, named after physicist Leon Cooper, who explained a related phenomenon in ordinary superconductors in the 1950s. Cooper pairing occurs when two fermions form a bound pair that behaves collectively as a boson. Bosons, unlike fermions, are not subject to the Pauli exclusion principle. Any number of bosons can occupy the same quantum state simultaneously. When a large fraction of the fermions in a system form Cooper pairs, and those pairs all condense into the same lowest energy quantum state, the result is a superfluid, a quantum condensate in which all the paired particles move as one coherent whole, without friction, without resistance, without dissipation. In a neutron star's outer core, the attractive component of the strong nuclear force at moderate range provides the mechanism for Cooper pairing. Two neutrons, interacting through the strong force, can form a bound pair. When conditions are right, the majority of the neutrons in the outer core pair up this way, and the resulting fluid of Cooper pairs becomes a superfluid. The entire vast ocean of neutron fluid, billions of tons of material spread across several kilometers, flows as a single coherent quantum entity. We have evidence that this is actually happening. The evidence comes from a peculiar observational phenomenon called a glitch. Neutron stars, particularly the pulsars, whose rotation rates we measure with great precision using radio telescopes, gradually slow down over time. This is expected. They radiate energy as they spin, and that energy has to come from somewhere, so their rotation gradually decelerates. But occasionally, the spin rate of a pulsar abruptly increases, jumping upward in a fraction of a second before slowly recovering over the following days or weeks. These jumps are called glitches, and the most widely accepted explanation for them involves the superfluid interior. The outer crust of a neutron star is a crystalline lattice that slows down gradually as the pulsar loses rotational energy. But a superfluid cannot slow down the same way. A superfluid can only rotate by forming quantized vortices, tiny whirlpools of circulation, each carrying a specific fixed quantum of angular momentum. As the crust decelerates, the superfluid interior maintains its rotation rate, building up a growing lag between the crust's spin and the superfluid spin. At some point, the vortices carrying the superfluid's angular momentum suddenly migrate outward and transfer a burst of angular momentum to the solid crust, spinning it up. This is a glitch. The solid and superfluid interior have briefly exchanged angular momentum, and the result is a sudden measurable jump in the star's observed rotation rate. The Vela pulsar, A neutron star, roughly 1,000 light-years from Earth, formed in a supernova explosion about 11,000 years ago, is one of the most prolific glitchers known. It experiences a major glitch roughly once every 3 years, each time jumping in rotation rate by about 1 part in a million. That fraction sounds small, but for an object spinning 11 times per second, with the moment of inertia of 2 solar masses packed into 12 kilometers, it represents an enormous transfer of angular momentum, and it is exactly the kind of event that the superfluid vortex model predicts. The protons in the outer core, though a minority, do something equally extraordinary. They form Cooper pairs through a slightly different mechanism and become superconducting. A superconductor is to electrical current what a superfluid is to fluid flow, a state in which resistance drops to exactly zero and current flows without any energy loss. In a neutron star's outer core, the superconducting proton fluid interacts with the star's magnetic field in ways that confine the field into quantized flux tubes, thin filaments of magnetic field threading through the superconducting medium. These flux tubes interact dynamically with the neutron superfluid's vortices, creating a coupled system of quantized structures that influences how the magnetic field evolves over millions of years, and how the star's internal dynamics couple to its observable spin behavior. The picture that emerges of the outer core is one of breathtaking complexity, an ocean of superfluid neutrons threaded with quantized vortex lines, interpenetrated by a smaller population of superconducting protons carrying quantized magnetic flux tubes, with a background of relativistic electrons maintaining electrical neutrality. 3 quantum fluids coexisting in the same volume at densities hundreds of trillions of times greater than anything achievable in a laboratory, spinning hundreds of times per second, threaded with magnetic fields 1 trillion times stronger than Earth's. Nothing in any terrestrial laboratory comes close to this. Nothing in any planetary environment in the solar system approaches it. It is matter in a state that exists nowhere in the natural world except here, in these city-sized remnants of stellar catastrophes scattered across the galaxy. And yet, extraordinary as the outer core is, it remains the region of the neutron star where our theoretical understanding is firmest. The outer core contains matter at densities of 1 to 2 times what physicists call normal nuclear density, the density found inside the nucleus of an ordinary atom. These are conditions we can at least approach through laboratory nuclear physics. We have studied nuclei. We have measured the strong force between nucleons in scattering experiments. We have developed sophisticated theoretical frameworks, nuclear many-body theory, chiral effective field theory, quantum Monte Carlo methods that allow us to extrapolate from laboratory measurements to the densities of the outer core with at least reasonable confidence. We cannot be certain our extrapolations are correct, but they are grounded in genuine knowledge. The inner core is different. The inner core is where the ground falls away beneath the physicist's feet. The inner core begins where densities exceed roughly twice normal nuclear density and may reach 5, 8, perhaps even 10 times normal nuclear density at the very center of the star. These are densities we have never directly probed in any experiment. They are densities that may never be achievable in any terrestrial laboratory. And at these densities, the matter may undergo transformations so profound that the very concept of a neutron, as a discrete particle with its own identity and internal structure, begins to dissolve. A neutron is not a fundamental particle. This is a crucial point. A neutron is a composite object, a bound state of 3 quarks, 1 up quark and 2 down quarks, held together by the strong nuclear force mediated by gluons. Under ordinary circumstances, these quarks are permanently confined within the neutron. You can never pull a single quark out of a neutron, no matter how much energy you apply. If you try, the energy you invest in stretching the quark-gluon field simply materializes into new quark-antiquark pairs, which immediately bind into new composite particles. The original quark never escapes. This phenomenon, called confinement, has been confirmed in every particle physics experiment ever performed. No free quark has ever been observed. But confinement is not a law of the universe in the deepest sense. It is a consequence of how the strong force behaves at the densities and temperatures that prevail everywhere in the observable universe under ordinary conditions. At extreme densities or temperatures, confinement can break down. We know this because we have seen it happen. At the Large Hadron Collider at CERN and at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, physicists have collided heavy nuclei together at nearly the speed of light and created, for tiny fractions of a second, temperatures exceeding several trillion degrees. At these temperatures, protons and neutrons dissolve. The quarks and gluons that were confined inside them break free and form a new state of matter called a quark-gluon plasma, a soup of liberated quarks and gluons moving freely through a volume much larger than any single nucleon. This has been experimentally confirmed. The quark-gluon plasma is real. Confinement is not inviolable, but the quark-gluon plasma produced in accelerators is extraordinarily hot. It exists for the briefest imaginable moment before the fireball expands and cools and the quarks reassemble into hadrons. The conditions inside a neutron star's inner core are fundamentally different. The temperature there, though millions of degrees by any human standard, is negligibly low compared to the energy scales of quantum chromodynamics. The neutron star inner core is cold and dense, while the collider fireballs are hot and briefly dense. These are different corners of the same phase diagram, and the physics in each corner can be quite different. The cold, dense corner is exactly where our theoretical tools break down most completely. The standard computational approach for quantum chromodynamics, called lattice QCD, which uses supercomputers to simulate quark and gluon behavior on a discrete spacetime grid, works beautifully at high temperatures and has been enormously successful in matching accelerator measurements. But at low temperatures and high densities, lattice QCD runs into a fundamental mathematical obstruction known as the fermion sign problem. The equations become effectively unsolvable. The computations that would otherwise be straightforward become so numerically unstable that reliable results cannot be extracted. This is not a matter of needing faster computers. It is not a solvable engineering challenge. It is a fundamental mathematical obstruction in the theory. Quantum chromodynamics is believed to be the correct and complete theory of the strong force, but we cannot solve it in the regime that matters most for the inner core of a neutron star. We have the right theory. We simply cannot extract the answer. So, what might be happening there? Physicists have developed several scenarios, each grounded in physical reasoning and theoretical extrapolation, none definitively confirmed. In the simplest scenario, the matter in the inner core remains in the form of neutrons all the way to the center. Even at 5 or 8 times nuclear density, the neutrons are compressed and overlapping, but they maintain their identity as discrete composite particles. The short-range repulsion of the strong force between quarks belonging to different neutrons prevents complete dissolution. The equation of state in this scenario is what physicists call stiff, meaning pressure rises sharply with increasing density, and the neutrons resist compression vigorously even at these extreme densities. In this picture, the neutron star is extreme but conceptually comprehensible, nuclear matter pressed to its limits, but still recognizable as the same basic stuff that fills atomic nuclei, just vastly more concentrated. In a second scenario, the inner core undergoes a phase transition to deconfined quark matter. At some critical density, the boundaries between neighboring neutrons simply cease to exist. The quarks that were confined within individual neutrons suddenly find themselves able to move freely through a volume spanning the entire inner core. There is no longer any meaningful distinction between one neutron and the next. The identity of individual nucleons dissolves. What remains is a cold, dense quark-gluon plasma, a sea of free quarks and gluons filling the innermost several kilometers of the star. This phase transition might be sharp and abrupt, a clear boundary at a specific density below which you have neutrons and above which you have free quarks. Or it might be a gradual crossover, a progressive dissolution of neutron identity over a range of densities rather than a sudden transformation. The distinction matters enormously for the observable properties of neutron stars, but our current theoretical tools cannot tell us which scenario nature prefers. A third possibility involves the strange quark. The quarks inside ordinary neutrons are up quarks and down quarks, the two lightest quark flavors. There are actually 6 quark flavors in total. The strange quark is the third lightest, with a mass roughly 20 to 40 times that of the light quarks. Under ordinary conditions, strange quarks are irrelevant to nuclear physics. The energy required to create them is too high. But at the densities in the inner core, the story may change. When up and down quarks are packed so densely that the energy cost of adding another up or down quark, forced by the Pauli exclusion principle into an already crowded energy level, exceeds the mass cost of producing a strange quark. Starting fresh in an empty energy level, it becomes thermodynamically favorable to introduce strangeness. The system lowers its total energy by spreading quark flavor across 3 species rather than 2. If this happens, the inner core contains strange quark matter, a roughly equal mixture of up, down, and strange quarks, forming a 3-flavor quark plasma. The physicist Edward Witten proposed in 1984 that strange quark matter might not merely be a phase produced under extreme pressure, it might be the absolute ground state of matter, lower in energy per nucleon than even iron, which we ordinarily consider the most stable form of nuclear matter. If Witten's hypothesis is correct, then ordinary matter as we know it, the protons and neutrons making up every atom in the universe, is metastable rather than truly stable. It persists not because it is the lowest energy state, but because it is separated from the true ground state by an energy barrier. Like a ball resting in a shallow valley on the side of a hill, it is stable against small perturbations, but would roll downhill to a lower resting place if given sufficient push. The implications of this are dizzying. If strange quark matter is the true ground state, then some neutron stars might not be neutron stars at all. They might be strange stars, objects made entirely of strange quark matter from their cores to their surfaces, with no crust, no pasta phase, no neutron fluid, just a smooth, sharp surface where strange quark matter meets the vacuum. Distinguishing a strange star from a conventional neutron star with our current observational tools is at the edge of what is possible, but future observations may make the distinction tractable. Beyond deconfined quarks and strange matter, theorists have proposed an even more exotic possibility: color superconductivity. Quarks, like electrons, are fermions, and under sufficient density, they too can form Cooper pairs, binding together through the strong force into boson pairs that can condense into a superconducting quantum state. But quarks carry a type of charge called color charge, the strong force analog of electric charge, and color comes in 3 types, conventionally called red, green, and blue. The pairing patterns available to quarks are therefore far more varied and more complex than those available to electrons. Several distinct color superconducting phases have been predicted, each with its own distinctive symmetry structure and physical properties. The most elegant of these is called the color-flavor locked phase, in which quarks of all 3 light flavors and all 3 color charges pair up in a maximally symmetric arrangement that simultaneously breaks multiple fundamental symmetries of quantum chromodynamics in a coordinated and mathematically beautiful way. The color-flavor locked phase has properties unlike anything observed in any terrestrial material. It is a perfect insulator for some types of charge while being a perfect conductor for others. It is simultaneously a superfluid and a superconductor in certain senses, and it may have exotic low-energy excitations unlike anything in the particle physics zoo. Whether it actually exists inside neutron stars remains unknown. But it is one of the most theoretically rich and beautiful possibilities that the physics of dense matter has ever generated. There is also the puzzle of hyperons. Hyperons are particles similar in structure to protons and neutrons, but containing one or more strange quarks. A lambda hyperon, for instance, contains 1 up, 1 down, and 1 strange quark. At sufficiently high densities, it may become energetically favorable for some of the neutrons in the inner core to convert into hyperons, introducing a new particle species into the nuclear fluid. This would soften the equation of state, reducing the pressure at a given density, making the star more compressible. And here lies the puzzle. Most equations of state that allow hyperons to appear predict maximum neutron star masses that fall below what we have actually observed. The most massive confirmed neutron stars weigh in at roughly 2 solar masses. Many hyperon-containing equations of state cannot produce a stable star at that mass. Something must be wrong with the calculation, or something must be pushing the maximum mass back up. But what? The answer is not yet known. These open questions, the nature of matter in the inner core, the presence or absence of quark deconfinement, the stability of strange quark matter, the resolution of the hyperon puzzle, are not merely academic puzzles. They are some of the deepest unresolved questions in fundamental physics. They touch on the behavior of the strong nuclear force in regimes that cannot be probed by any existing or planned accelerator. They touch on the nature of matter at the most extreme densities the universe can stably sustain. And answering them requires not just better theory, but better observation, because neutron stars are the only places in the universe where these conditions naturally exist and persist over timescales long enough to study. The question, then, is how to read the interior of a neutron star from the outside. How to extract information about matter at 5 or 8 or 10 times nuclear density from the signals that travel across thousands of light years to reach us. The answer, it turns out, lies in several different measurement strategies, each probing a different aspect of the neutron star's structure, each providing a different piece of the puzzle. The most direct constraint comes from mass measurements. If you know how heavy a neutron star can be, you immediately eliminate any equation of state that predicts a lower maximum mass. The mass of a neutron star in a binary system can be measured with exquisite precision using the timing of radio pulses. When a pulsar is in a binary orbit with a companion star, the timing of its pulses is subtly shifted by the Doppler effect as the pulsar moves toward and away from Earth, and by gravitational effects as the pulses pass through the curved spacetime near the companion. Analyzing these timing variations allows physicists to determine the masses of both objects in the binary with extraordinary precision. The technique has yielded mass measurements accurate to tiny fractions of a solar mass for dozens of pulsars. The most massive confirmed neutron star currently known has a mass of approximately 2.1 solar masses, measured through this technique. This single observation rules out vast swaths of theoretical equation of state space. Any model that predicts nuclear matter becomes too soft at high densities, unable to support this mass against gravitational collapse, is definitively ruled out. Many models that include early onset of quark deconfinement or hyperons are eliminated by this constraint. The universe has given us a hard lower bound on how stiff the nuclear equation of state must be. Radius measurements provide complementary and independent information. A stiffer equation of state, one where pressure rises more sharply with density, produces a larger, more inflated neutron star. A softer equation of state produces a smaller, more compact one. Measuring the radius of a neutron star, even roughly, therefore constrains the equation of state from a different direction than mass measurements do. Measuring a neutron star's radius is technically challenging. The stars are very small and very far away, too small to resolve their disks with any existing telescope. But there are indirect methods. The most powerful is analyzing the X-ray emission from neutron stars that have hot spots on their surfaces, regions that are hotter than the average and therefore brighter. As a neutron star rotates, these hotspots sweep in and out of view, producing characteristic brightness variations. The shape of these variations is distorted by the star's intense gravity, which bends the light emitted from the surface. By modeling these distortions carefully, accounting for the way strong gravity curves the paths of photons near the surface, it is possible to extract both the mass and the radius of the star simultaneously. NASA's Neutron Star Interior Composition Explorer, an X-ray telescope mounted on the International Space Station, was designed precisely for this purpose. Its initial results, published in the early 2020s, suggest radii in the range of 12 to 13 kilometers for neutron stars of about 1.4 solar masses. This is consistent with a moderately stiff equation of state, neither soft enough to produce very small stars, nor stiff enough to produce very large ones. Combining these radius measurements with the mass measurements from pulsar timing, the allowed region of equation of state space is being progressively narrowed, though much uncertainty remains. The most dramatic observational breakthrough in neutron star physics came on the 17th of August, 2017. On that morning, gravitational wave detectors in the United States and Europe registered a signal unlike any they had seen before. The signal lasted about 100 seconds, a long, sweeping chirp as two neutron stars spiraled toward each other and merged. The event was designated GW170817, and it changed everything. Previous gravitational wave detections had involved black holes, objects with no matter, no surface, nothing to see in electromagnetic light. GW170817 was different. Neutron stars have matter, and matter, when compressed and heated and detonated in a merger, glows. Within seconds of the gravitational wave detection, alert systems sent notifications to hundreds of observatories around the world. Within hours, 70 telescopes on every continent and in space had turned toward the source, a galaxy called NGC 4993, about 130 million light-years from Earth. What they found there was extraordinary. The merger had produced a short gamma-ray burst, a brief, intensely energetic flash of gamma radiation that had been traveling toward Earth for 130 million years and arrived just 1.7 seconds after the gravitational wave signal. This confirmed a long-standing theoretical prediction that the collision of two neutron stars is the engine that powers short gamma-ray bursts, brief cosmic detonations that had been observed for decades without a definitive source identification. In the days and weeks following the merger, telescopes watched as the debris from the collision glowed and evolved. This optical and infrared glow, called a kilonova, carried chemical information in its spectrum, direct evidence that the collision had synthesized heavy elements. The synthesis of heavy elements in neutron star mergers had been theorized for decades. The problem is simple to state. Nuclear fusion in stars can build elements up to iron. Elements heavier than iron cannot be made by fusion because the reactions do not release energy. Yet the universe is full of heavy elements: gold, platinum, lead, uranium, thorium, the rare earth elements that fill the bottom 2 rows of the periodic table. These must be made somewhere. The most promising mechanism is a process called rapid neutron capture, or the IR process, in which nuclei are bathed in an intense flux of neutrons and capture them faster than they can decay, building up very neutron-rich, very heavy nuclei that eventually shed their excess neutrons through beta decay to produce stable, heavy isotopes. A neutron star merger, with its extreme neutron densities and violent dynamics, is exactly the kind of environment where the R process can operate at full intensity. The spectrum of the GW170817 kilonova showed the signatures of lanthanide elements, the heavy rare earth metals that can only be produced by the R process. It was direct visual confirmation that the gold in rings and necklaces worn by human beings on Earth was forged in a neutron star collision billions of years ago, scattered through the interstellar medium in the debris cloud, swept up into the gas cloud that formed the solar system, concentrated in Earth's crust by geological processes, and eventually mined and shaped by human hands. The gold you can hold in your hand carries the memory of a cosmic catastrophe. The gravitational wave signal from GW170817 also carried detailed information about the neutron star's internal structure, encoded in a subtle characteristic of the final moments before the merger. As the two stars drew closer together, each was distorted by the tidal gravitational field of the other, stretched and compressed as the tidal forces grew stronger. The degree of this tidal distortion, called the tidal deformability, depends directly on the equation of state. A star that is easy to distort, that stretches dramatically under tidal forces, has a soft equation of state. A star that resists distortion and maintains its shape has a stiff one. The tidal distortion imprints itself on the frequency and amplitude of the gravitational wave signal during the final seconds before merger, and LIGO was sensitive enough to measure it. The measurement showed that the stars were moderately deformable, ruling out the most extreme possibilities in both directions. Extremely stiff equations of state, predicting very large and rigid stars, were disfavored. Extremely soft equations of state, predicting very small and squishy stars, were also disfavored. The universe was narrowing the range of possibility, telling us through the medium of gravitational waves something about the physical nature of the matter compressed inside neutron stars. Future gravitational wave observations promise to narrow it still further. Next-generation detectors, currently in the planning and early design stages, will be roughly 10 times more sensitive than the instruments that detected GW170817. They will detect hundreds or thousands of neutron star mergers per year, rather than the handful we can currently observe. Each merger provides an independent measurement of tidal deformability. Each measurement constrains the equation of state from a slightly different angle. With a large enough statistical sample, it should be possible to discriminate between equations of state that differ in subtle ways, perhaps even to distinguish between scenarios with and without quark deconfinement in the inner core. There are also subtler but extraordinarily precise tests available from studying pulsars over long time periods. Millisecond pulsars, neutron stars spun up to hundreds of rotations per second by the accretion of material from a companion star, are among the most precise natural clocks in the universe. Their pulse timing can be measured with accuracy comparable to atomic clocks. In binary systems, the gradual orbital decay caused by gravitational wave emission, the accumulated Shapiro delay from gravitational time dilation, the advance of the orbital periastron due to general relativistic precession, all of these effects can be measured over years and decades with extraordinary precision, testing general relativity in strong field conditions and providing tight constraints on neutron star masses. The precision of these measurements is genuinely remarkable. Some pulsar mass determinations have uncertainties smaller than 0.5%. Multi-messenger astronomy, the combination of gravitational wave, electromagnetic, and neutrino observations of the same events, is transforming our ability to study neutron stars. Each messenger carries different information. Gravitational waves probe the tidal structure and dynamics of the merger. Electromagnetic light from the kilonova probes the chemical composition of the ejecta and the nature of the R process. Neutrinos, if we are close enough to detect them, probe the core dynamics and the formation of the remnant. A future galactic supernova, occurring within our own galaxy, would produce a neutrino burst detectable by multiple instruments simultaneously, offering a real-time window into the moments of neutron star birth. All of these observational threads converge on the same fundamental question: what is matter when it is pushed to the edge of what it can endure? What happens when you take the building blocks of everything that exists and compress them harder than they were ever designed to be compressed? The neutron star sits at the boundary of the answer. Its outer layers tell us about matter at densities already far beyond anything terrestrial. Its inner core, inaccessible to direct observation, holds the deepest secrets about the nature of matter at the most extreme stable densities the universe can produce. There is something poignant about the way we study these objects. We cannot visit them. We cannot even resolve their disks with any existing telescope. They are city-sized objects scattered across distances of thousands of light years. The closest known neutron star is perhaps a few hundred light years away, still an unreachable gulf by any human measure. We study them entirely through their emissions: radio pulses from their rotating magnetic fields, X-rays from their hot surfaces and from material falling onto them, gamma rays from their most violent episodes, gravitational waves from their mergers, neutrinos from their births. Each emission is a message, encoded in physics, transmitted across the galaxy, arriving at our detectors after journeys of years or centuries or millennia. Reading those messages requires building instruments of extraordinary sensitivity: kilometer-scale interferometers for gravitational waves, X-ray telescopes in orbit above the absorbing atmosphere, radio dishes spanning continents in arrays that achieve angular resolution comparable to planet-sized telescopes, underground neutrino detectors filled with thousands of tons of ultra-pure water or ice. Each of these instruments represents decades of effort by thousands of scientists and engineers working at the absolute frontier of what human technology can achieve. And yet, the universe cooperates. It has scattered neutron stars across the galaxy in sufficient numbers that there are targets to study. It has arranged some of them in binary systems that make precise mass measurements possible. It has aligned some of them so that their radio beams sweep across Earth, giving us exquisitely timed signals to analyze. It has allowed two of them to spiral together and merge within the reach of our first-generation gravitational wave detectors, giving us a glimpse of the kilonova and the gravitational wave signal that together constrain the equation of state in ways we could not have achieved by any other means. The universe is, in a sense, showing us its interior. We just have to be clever enough to read the light. What we have learned, pieced together from pulsar timing and X-ray observations and gravitational wave measurements and nuclear theory, is a picture of stunning complexity. Matter inside a neutron star is not a single substance in a single state. It is a nested sequence of phases, each more extreme than the last, each governed by a different balance of forces, each representing a different answer to the question of what happens to matter when you compress it harder than nature does anywhere else. The crystalline crust with its exotic neutron-rich nuclei, the pasta phases in the transition zone, the superfluid neutron ocean of the outer core, the proton superconductor, and then, in the depths, the inner core, where everything we have learned may apply and may not, where the matter may remain as neutrons or may have dissolved into free quarks or something stranger still. The neutron star is 12 kilometers across. You could walk its entire circumference if you could somehow survive on its surface in a few hours. It contains more mass than the sun. Its gravity would kill you before you arrived. Its magnetic field would destroy every chemical bond in your body from a distance of 1,000 kilometers. And inside it, at its center, in conditions we cannot create, in a regime our best theory cannot solve, in a state of matter that may have no name in any human language, the universe is doing something we do not yet fully understand. This is not a failure, it is an invitation. Every field of science has a frontier, a boundary where the known ends and the unknown begins. In physics, that boundary moves. It has been moving for as long as human beings have asked questions about the natural world. The frontier is always where the action is, where the most interesting discoveries wait, where the equations run ahead of intuition and nature turns out to be stranger and richer than anyone expected. The interior of a neutron star is one of those frontiers today. The inner core, with its ambiguous matter and its unsolvable equations, is the place where our understanding of the strong nuclear force is genuinely incomplete, where the physics of the universe has not yet been fully written down in human language. But the frontier is not fixed. The gravitational wave detectors are running. The X-ray telescopes are watching. The radio arrays are listening. The theorists are working. The answers are being pursued with every tool that exists and with new tools being invented. The story of neutron stars is not a closed book. It is an open investigation conducted simultaneously by thousands of people working at the edge of what is known, reading the signals that ancient stellar deaths have been broadcasting across the galaxy since before human civilizations existed. Somewhere in the Milky Way, a neutron star is spinning. It has been spinning since the day it formed in the catastrophic collapse of a star that died perhaps 1 million years ago, or 10 million, or 1 billion. Its surface is scarred by the violence of that birth. Smooth now and featureless, hotter than any surface in the solar system, except for the most violent solar flares. Its interior is a layered labyrinth of exotic matter, each layer stranger than the one above. At its center, matter is doing something extraordinary, something that may involve the liberation of quarks that have been confined inside individual particles since the first microseconds after the Big Bang, something that may represent the deepest form of matter the universe is capable of producing without tipping into a black hole. The neutron star spins, it radiates. It sends its signals out into the dark, across the parsecs, toward whatever instruments and whatever intelligences might be positioned to receive them. It has been broadcasting for 1 million years. We have been listening for about 60. What we have heard already has transformed our understanding of matter, of gravity, of the fundamental forces that structure the universe. What we have not yet heard, what lies encoded in the signals we have not yet been able to decode, may transform it again. The universe built these objects to answer a question it has been asking since matter first condensed out of the energy of the Big Bang. How far can you push before everything changes? The neutron star sits at that boundary, balanced between the known and the unknown, between matter and its dissolution, between the physics we have learned and the physics we have yet to discover. It is the universe's answer to the question, and we are still learning how to read it. The story is not over. It may be just beginning. To understand just how profoundly strange this situation is, consider for a moment what it means to say that we do not know what matter looks like at the center of a neutron star. This is not a gap in our knowledge in the ordinary sense, like not knowing the exact population of a distant city or the precise chemical composition of a remote asteroid. The uncertainty about neutron star cores is uncertainty about something fundamental, the behavior of the building blocks of all visible matter under conditions that are physically realized right now, at this moment. in objects that exist in our own galaxy. The matter at the center of a neutron star is not hypothetical. It is not a thought experiment. It is real matter, sitting in a real place, governed by the real laws of physics. And we do not know what it looks like. This is one of the remarkable features of living at this moment in the history of science. We have a theory of the strong nuclear force, quantum chromodynamics, that is among the most precisely tested and mathematically rigorous theories in the history of physics. It has been confirmed by thousands of experiments across dozens of particle accelerators over more than 50 years. Its predictions match experimental measurements to extraordinary precision. In almost every regime where we can compute its consequences and compare them to observations, it works. And yet it refuses to yield its secrets about dense cold matter. The mathematics of the theory in that regime is intractable. The equations are there. The theory is right. We just cannot solve it where it matters most. There is something almost paradoxical about this situation. In many areas of science, the limiting factor is not theory, but data. We have theoretical frameworks that are more powerful than our ability to test them. In the physics of dense matter inside neutron stars, the situation is the reverse. We have extraordinary data. Pulsar masses measured to better than 1%. Radius estimates converging toward the 12 to 13 kilometer range. Tidal deformability measurements from gravitational wave events. Cooling observations from young neutron stars. Spin-down rates and glitch behaviors from decades of pulsar monitoring. What we lack is the theoretical ability to turn that data into definitive answers about the microphysics of the core. Progress is being made, though, not through a single dramatic breakthrough, but through the steady accumulation of constraints from many directions simultaneously. Each new pulsar mass measurement rules out another class of equation of state. Each new radius determination from the NISR telescope narrows the range further. Each new gravitational wave event from merging neutron stars adds another data point on tidal deformability. The pressure of all these observations, coming from so many different directions, is slowly squeezing the allowable region of equation of state space into a smaller and smaller shape, like closing in on a solution from all sides at once. Nuclear theorists are also making progress from within. New computational methods for nuclear many-body theory, developed over the past 2 decades, have extended our reliable theoretical knowledge of nuclear matter to higher densities than was previously possible. Methods rooted in chiral effective field theory, which connects the fundamental quark and gluon description of nuclear forces to the more practical neutron-neutron and proton-neutron interactions relevant for neutron star matter, have pushed the reliable regime upward toward twice nuclear density and are being extended further. Monte Carlo methods for solving quantum mechanical many-body problems have become more powerful as computational resources have grown. The envelope of what we can calculate is slowly expanding. There is also a growing body of work using sophisticated machine learning techniques to explore the space of possible equations of state in a more systematic way. By treating the equation of state as an unknown function and using Bayesian statistical methods to update the probability distribution over possible equations of state as new data arrives, physicists can extract more information from the available observations than traditional methods allow. The resulting constraints, while still uncertain, are becoming increasingly informative, but the ultimate test will come from direct observations sensitive enough to discriminate between the deepest theoretical possibilities. An observation that definitively rules out quark deconfinement in the inner core, or conversely confirms it, would be one of the major scientific achievements of the century. It would tell us something fundamental about the phase structure of quantum chromodynamics, about the nature of confinement, about whether the quarks that were liberated in the first microseconds after the Big Bang and then confined inside protons and neutrons as the universe cooled can ever be liberated again under cold, dense conditions, not just in the fireball of a heavy ion collision, but in the quiet, stable heart of a city-sized stellar remnant. The detection of quark matter in neutron stars would also have profound implications for our understanding of the early universe. In the first microseconds after the Big Bang, the entire observable universe was hotter than the temperatures produced at any accelerator and denser than any neutron star. All matter existed as a quark-gluon plasma. The transition from that primordial plasma to the confined hadrons we see today called the QCD phase transition, happened when the universe was perhaps 10 microseconds old. Understanding the phase structure of quantum chromodynamics, understanding exactly where and how the transition from deconfined to confined matter occurs, is directly relevant to understanding this earliest epoch of cosmic history. Neutron stars, in their own way, are windows into the physics of the very early universe. There is a philosophical dimension to this that goes beyond the technical details of nuclear physics. When physicists study the interior of a neutron star, they are probing the same fundamental physics that governed the universe in its first moments. The quark-gluon plasma in the cores of the most massive neutron stars, if it exists, is a remnant in a sense, matter that has been returned to the conditions of the primordial universe under the pressure of a collapsed star's gravity. The neutron star is not just an extreme object in the present-day universe. It is, in its deepest parts, an echo of the very beginning. Consider also what a neutron star's existence implies about the universe's tolerance for complexity. The conditions inside a neutron star are, by any ordinary measure, violently inimical to structure, to complexity, to the kinds of organized systems we associate with life, or chemistry, or technology. The temperature is millions of degrees. The density exceeds anything achievable in any laboratory. The gravity would annihilate any molecular structure instantly. And yet, inside this apparent chaos, extraordinary order exists. The crystal lattice of the outer crust is a perfectly organized geometric structure. The superfluid neutron ocean flows in perfect quantum coherence. The quantized vortices and flux tubes threading through the core form organized structures governed by precise mathematical rules. The nuclear pasta of the transition zone takes on geometrically beautiful forms, dictated by the competition between fundamental forces. Order, it turns out, is not just a feature of mild conditions. It is a feature of the universe at every scale of energy and density. Wherever you look, at whatever extreme, the laws of physics produce organized, structured, beautiful configurations of matter. The neutron star is no exception. It is, in its own way, as organized and as structured as a living cell, but governed by entirely different principles, at entirely different scales, made of entirely different stuff. The neutron star also invites reflection on the role that death plays in the cosmos. Every neutron star began as a living star, a star that burned steadily for millions of years, fusing hydrogen into helium into carbon and on through the periodic table. The death of that star, the collapse of its core, the supernova explosion that scattered its outer layers across tens of light years, the formation of the compact remnant spinning in the debris, was not just an ending. It was a transformation. The material blown off in the supernova enriched the interstellar medium with heavy elements forged in the star's interior over its long life. Those elements became the raw material for future generations of stars and planets. The neutron star itself, dense and permanent and broadcasting across the galaxy, became a laboratory for physics that could not have existed in the original star. Life on Earth, and presumably wherever else in the universe conditions have allowed complex chemistry to emerge, is built from elements forged in stellar interiors and scattered in stellar explosions. The carbon in your body was made in a star that died before the sun was born. The iron in your blood was forged in a supernova billions of years ago. The calcium in your bones, the oxygen you breathe, the nitrogen in your DNA, all of it was once inside a star, once compressed in a stellar core, once carried outward in the shock wave of a stellar death. You are, in the deepest sense, made of the debris of stellar catastrophe. And the neutron stars that remain after those catastrophes are not just relics. They are active participants in the ongoing story of the cosmos. Some accrete material from companion stars, occasionally erupting in X-ray bursts as accreted hydrogen flashes into nuclear burning on their surfaces. Some merge with other neutron stars, producing gravitational wave events and kilonovae that scatter freshly synthesized heavy elements into the interstellar medium. Some spin down over billions of years as their magnetic fields weaken and their rotation decelerates. Some sit alone in the dark, cooling slowly, carrying their interior secrets across the eons. The magnetars, those neutron stars with the most extreme magnetic fields, are particularly dramatic in their behavior. Occasionally, a magnetar experiences a sudden, catastrophic rearrangement of its crust or magnetic field, releasing in a fraction of a second as much energy as the sun radiates in 100,000 years. These events, called giant flares, are detectable across the entire observable galaxy, and even, for the most powerful events, across millions of light-years in neighboring galaxies. The most powerful magnetar flare ever observed, in December 2004, briefly overwhelmed the sensors of multiple space-based X-ray and gamma-ray instruments, despite originating from a source 50,000 light-years away in our own galaxy. For a fraction of a second, a single event on a spinning star halfway across the Milky Way affected instruments orbiting Earth. The energy flux at our location was, for that moment, comparable to a brief extra sun. Understanding what causes these giant flares, whether they involve catastrophic failure of the nuclear pasta in the crust, sudden reorganization of the magnetic flux tubes in the superconducting core, or some other mechanism, requires understanding the interior structure of the star in detail. It requires knowing the mechanical strength of nuclear pasta, the dynamics of quantized vortex lines and flux tubes, the coupling between the superfluid neutron fluid and the solid crust. The interior physics is not just an abstract puzzle. It manifests in observable, dramatic events whose signatures cross the galaxy. Neutron stars and binary systems display an even richer phenomenology. When a neutron star has a companion star close enough that material flows from the companion onto the neutron star, the infalling material forms an accretion disk that heats and glows in X-rays. The neutron star becomes an X-ray binary, potentially one of the brightest X-ray sources in the galaxy. The accreted hydrogen and helium sometimes builds up on the surface until it reaches the ignition temperature for thermonuclear burning, then flashes suddenly in a thermonuclear runaway called an X-ray burst. The X-ray burst produces a brief but intense spike in luminosity as a thin layer of nuclear fuel burns across the entire surface of the star in a few seconds, reaching temperatures of perhaps 2 billion degrees. The spectral characteristics of this burning layer carry information about the surface gravity of the star, and therefore about its mass-radius relationship, providing yet another indirect probe of the equation of state. In some X-ray binaries, the neutron star is close enough to its companion that the accreted material transfers angular momentum as well as mass, spinning the neutron star up to millisecond rotation rates over millions of years. This is how millisecond pulsars are created, normal pulsars that have been spun up by accretion to hundreds of rotations per second, then left spinning rapidly when the accretion ends. Their rapid rotation makes them extraordinarily precise natural clocks, useful for timing experiments of remarkable sensitivity. Arrays of millisecond pulsars scattered across the galaxy are being used as gravitational wave detectors in their own right, sensitive to gravitational waves of much lower frequency than Li, GO, and Virgo can detect. Changes in the timing of pulsar pulses, correlated across multiple pulsars, can reveal the presence of gravitational waves with periods of years to decades. These pulsar timing arrays are currently showing hints of a gravitational wave background, a sea of gravitational waves from the mergers of supermassive black holes in the cores of galaxies across the observable universe. The neutron star, then, is not just an object of intrinsic scientific interest. It is a tool. Its extraordinary stability as a rotating clock makes it useful for testing general relativity. Its sensitivity to tidal effects makes it a probe of nuclear physics. Its merger signatures make it a source for gravitational wave astronomy. Its X-ray emissions make it a probe of hot plasma physics. Its cooling behavior makes it a probe of neutron star thermal transport. Virtually every aspect of its behavior tells us something we could not learn any other way. The diversity of neutron star types is itself scientifically valuable. There are rotation-powered pulsars, which radiate because they spin and slow down, losing rotational energy as electromagnetic radiation. There are accretion-powered X-ray pulsars, which radiate because material falls onto them from a companion star. There are magnetars, which radiate primarily from the energy stored in their extraordinary magnetic fields. There are central compact objects and supernova remnants, young neutron stars and the debris of recent stellar deaths. There are isolated neutron stars that appear to emit only thermal radiation from their cooling surfaces. Each type offers a different window into different physical processes, and studying the full range of types allows us to triangulate toward a complete picture. The youngest neutron stars, those still glowing in the remnants of the supernovae that created them, are particularly scientifically rich. They are hot enough that the thermal emission from their surfaces is detectable, and the spectral shape of that emission carries information about the composition of the outermost layers, whether the surface is mostly iron or carbon or some mixture. Changes in the surface temperature over time, as measured by X-ray telescopes over years and decades, reveal how quickly the star is cooling, which depends on the thermal conductivity of the crust, the presence or absence of exotic particles in the core, and the neutrino emission rates from deep inside the star. Cooling curves for young neutron stars have already provided important constraints on the presence of exotic particles that would accelerate cooling. Some neutron stars appear to cool faster than standard models predict, possibly indicating enhanced neutrino emission from the presence of hyperons or quark matter in the core. The Cassiopeia, a neutron star, a young neutron star in a supernova remnant about 11,000 light-years from Earth, was observed to cool at a measurable rate over roughly a decade of X-ray telescope observations. The cooling appeared to accelerate around 2010, an effect that some theorists interpreted as evidence for the onset of neutron superfluidity in the core. When the neutrons first form Cooper pairs, the transition releases latent heat and then allows enhanced neutrino cooling, producing a temporary spike in cooling rate. If this interpretation is correct, it would be direct observational evidence of a quantum phase transition occurring inside a neutron star, a real-time observation of exotic nuclear physics in action at a distance of 11,000 light-years. The interpretation remains debated, as many of the most exciting observations in this field do, but the debate itself is productive. It forces theorists to sharpen their predictions, to identify which observational signatures distinguish different theoretical scenarios, to develop new calculations that can be tested against the growing body of data. Science advances through exactly this kind of productive tension between observation and theory, between the signals the universe sends and our attempts to decode them. There is a certain humility required in studying neutron stars. These objects were theorized for decades before the first pulsar was discovered in 1967. Even after their discovery, it took years for the community to accept that pulsars were rotating neutron stars rather than some other exotic phenomenon. The theoretical prediction of neutron star existence came in the 1930s from Fritz Zwicky and Walter Bode, who proposed in 1934 that stellar cores might collapse to form objects composed entirely of neutrons. They were right, but it took more than 30 years to find the first one. The history of neutron star physics is full of theoretical predictions that were initially skeptically received and later confirmed by observation, and of observational discoveries that confounded theoretical expectations and forced new thinking. Magnetars, for instance, were not predicted before they were discovered. The existence of neutron stars with magnetic fields, many orders of magnitude stronger than ordinary pulsars, was not anticipated. When anomalous X-ray pulsars and soft gamma-ray repeaters were discovered in the 1990s and identified as magnetars, it required a significant extension of the theoretical framework for neutron stars to explain their behavior. The discovery of millisecond pulsars in the early 1980s was similarly surprising. The idea that a pulsar could be spun up to hundreds of rotations per second by accretion from a companion star had been proposed theoretically, but the discovery of pulsars actually rotating at this rate was initially startling. The history teaches a lesson about the complexity of the universe. Nature is always richer than our models. Every time we have thought we understood neutron stars reasonably well, they have shown us something new. There is no reason to believe this has stopped. The next generation of telescopes and detectors will almost certainly reveal neutron star phenomena that are not currently anticipated, that will require new theoretical frameworks, that will teach us things about the universe we did not know to wonder about. The Einstein telescope, planned for construction in Europe, and the Cosmic Explorer, proposed for the United States, will be gravitational wave detectors roughly 10 times more sensitive than the current LIGO and Virgo instruments. At that sensitivity, they will detect neutron star mergers, not by the handful but by the thousands per year. Each event is a data point. Each data point is a new measurement of tidal deformability, a new constraint on the equation of state. The statistical power of 1,000 events is vastly greater than the power of a few. The equation of state will be mapped to a precision that is currently unimaginable. The Square Kilometre Array, a radio telescope under construction in South Africa and Australia, with a total collecting area of a square kilometre, will discover thousands of new pulsars and measure the properties of known pulsars with unprecedented precision. The resulting pulsar census will provide a statistical sample of neutron star masses and spin behaviors rich enough to reveal population-level patterns that are invisible in the current, smaller sample. It will also allow the pulsar timing array gravitational wave detection to reach definitive sensitivity, either confirming or ruling out the gravitational wave background signals currently being tentatively detected. Next-generation X-ray telescopes with larger collecting areas and better spectral resolution than current instruments will improve radius measurements from surface emission and from X-ray burst spectroscopy. They will allow the NISR-style mass radius measurements to be extended to many more neutron stars, building up a statistical picture of how radius varies with mass across the population. If the equation of state is stiff, all neutron stars will be roughly the same size regardless of mass. If it is soft, the radius will decrease with increasing mass. The shape of the mass radius curve is a direct signature of the equation of state, and then there are measurements we cannot yet imagine, from instruments not yet built, using techniques not yet devised. The history of astronomy is the history of new windows opening onto the universe. Radio astronomy, X-ray astronomy, gamma-ray astronomy, gravitational wave astronomy, each opened in turn, each revealing phenomena invisible through all previous windows. There is no reason to think the series is complete. Each new window has transformed our understanding not incrementally, but fundamentally. The neutron star, already transformed from a theoretical curiosity to a multi-messenger laboratory, may be transformed again by whatever windows open next. The universe is approximately 13.8 billion years old. For most of that time, there have been neutron stars spinning in the dark, accumulating angular momentum from infalling material, cooling slowly toward the cosmic microwave background temperature, sending their signals out across the galaxy. Some of the pulsars we observe today are genuinely ancient. Millisecond pulsars, spun up by accretion, and then long-lived because their rapid rotation decays only slowly, can persist for billions of years. Some of the millisecond pulsars we observe may have been spinning at hundreds of rotations per second since before the Earth existed. When we listen to a pulsar with a radio telescope, we are receiving a signal that has traveled for perhaps hundreds or thousands of years across interstellar space, originating from an object that has been spinning without pause for millions or billions of years, carrying inside its 12-kilometer body a form of matter that may have been in that state since the star's death, compressed to densities not seen in the universe since the first microseconds after the Big Bang. The act of detecting a pulsar pulse, that fraction of a second blip in a radio telescope's data stream, is an act of connection across unimaginable distances and timescales, a thread of information running from the extreme physics of a stellar remnant through the vacuum of interstellar space to the instruments of a civilization that has been doing science for a few centuries. There is a profound asymmetry here. The neutron star is indifferent. It does not know we are watching. It does not know its signals are teaching us about quantum chromodynamics and the equation of state of dense nuclear matter. It has been doing what it does for millions of years before there were any minds to observe it, and it will continue doing it for billions of years after whatever civilizations have arisen to study it have passed away. The physics it embodies is eternal. The laws of nature are eternal. The questions we are asking about matter and force and the structure of the universe at the deepest level are questions the universe itself embodies in every neutron star, regardless of whether anyone is there to ask them. But someone is there to ask them, and that is not nothing. We are a species that evolved on a small rocky planet orbiting an ordinary star in a backwater spiral arm of a medium-sized galaxy. Our entire history as a technological civilization spans a few thousand years. Our ability to study neutron stars spans less than 60. And in those 60 years, we have extracted an extraordinary amount of information from objects that are 12 kilometers across, thousands of light years away, and made of matter that exists nowhere else in the universe. We have measured their masses to fractions of a percent. We have estimated their radii to within a few kilometers. We have detected the gravitational waves from their mergers and measured their tidal deformability. We have watched them glitch and interpreted those glitches in terms of superfluid quantum mechanics. We have watched them cool and interpreted that cooling in terms of the onset of quantum phase transitions. We have watched the light of a neutron star merger and recognized in its spectrum the signatures of heavy elements being forged in real time. We have found gold and platinum and uranium, and we have traced their origin to the collisions of objects 12 kilometers across, occurring at speeds close to the speed of light. This is extraordinary. This is what science is. Not the accumulation of facts, but the progressive opening of understanding, the gradual illumination of the universe's secrets by minds that have no reason to expect the universe to be understandable, but pursue the understanding anyway, and find, to their perpetual astonishment, that it is. The neutron star spins. It has been spinning for 1,000,000 years. It will spin for another 1,000,000,000. Its interior holds secrets that have not yet been fully revealed, but we are listening, and we are getting closer, and the day will come when we know, with confidence, what matter looks like when the universe pushes it as far as it can go without crossing into the darkness of a black hole. That knowledge will not change the neutron star, but it will change us. It will deepen our understanding of what the universe is made of, what forces govern its deepest structure, and what nature is willing to do when given enough mass, enough gravity, and enough time. The story of the neutron star is not finished. It is one of the great open stories of science unfolding in real time, one observation at a time, one calculation at a time, one discovery at a time. And the ending, when it comes, will almost certainly surprise us. Because the universe, as every chapter of its story has demonstrated, is always stranger and always richer and always more beautiful than anyone thought to imagine.